So, hello everyone to this final lecture for today. Now we will have an invited tutorial, Ariel Bendersky, and he is going to talk to us about descriptive complexity and how it can be a tool to study quantum correlations. So, Ariel, thank you very much, and I guess you can start the tutorial.
Well, thank you for the introduction. I would like to first thank the organizers. If it was difficult in this context to prepare a talk, I can't imagine how difficult it was to set up this whole event. So thank you for that.
Thank you very
So I
much.
will be talking about descriptive complexity as a tool for quantum correlations. What's descriptive complexity? It's just the same as algorithmic complexity or Kolmogorov complexity, which is a measure of information that I will start talking right now. So first, as a motivation, let me tell you about the usual tale of non-locality. The usual tale goes as follows. We have Alice and Bob. They get boxes from an untrusted provider. And each of the boxes has a binary input and a binary output. This can be generalized to other scenarios. We can just stick to the simplest one, which is this THSH scenario. So after they get the boxes from the untrusted provider, Bob moves to a different planet, somewhere, anywhere in the universe. And then both of them start entering bits to their boxes, through the buttons they have on the boxes. We'll call X Alice's inputs and Y for Bob's inputs. And they start writing down the outputs they get from the boxes, A for Alice and B for Bob. So after repeating this many times, Bob sends his notebook to Alice. Alice takes her notes and what she got from Bob, and she just proceeds to analyze the probability of obtaining AB at the outputs, given that they have XY at the inputs. She measures this probability as the relative frequency of obtaining AB on the experiments, given that the inputs were XY. And as it doesn't violate the Bell inequality in the case of the boxes she had, they conclude that the boxes were local in this example, which means that the probability can be decomposed as this linear combination of probabilities for Alice and for Bob, these local probabilities. So they conclude that there's nothing strange about the boxes they had, so they don't write a paper or anything, and they just live happily ever after. So this is the usual tale about non-locality. I'm actually telling the tale about locality here, because they have local boxes. But there are some details we are missing. So what's the other side of this story? Let's imagine that at the time Alice was playing with the box, she was reading some short stories by Silvina Ocampo, who is a great writer. So instead of using random bits for her inputs, she decided to input one of these stories written in binary to her box. Bob was more of a boring person, so he just tossed a coin to decide his inputs. So when Alice received Bob's notebook and started analyzing, she kept analyzing it for a while because she wasn't convinced that the boxes were local. And just by chance, after a while, she decided to run on her computer the following command: unzip Bob's bits. So she took Bob's bits and ran the unzip, the uncompressor. And she was quite surprised because she realized that Bob's output bits were just a compressed version of the story Alice was reading. So actually the boxes were signaling, but they didn't realize at first because they were just looking at this probability, but they were signaling in a more convoluted way. So what's the moral of this story? If the provider is untrusted, as is the case, we shouldn't just analyze the probability of AB given XY, because maybe the boxes are doing some more convoluted stuff, okay? They are not just providing IID variables. So this is the motivation for what I'm going to tell you during this tutorial. okay? I forgot to tell you that if you want to interrupt with questions, I'm okay with that. Okay, so what will this tutorial be about? First, I will review a couple of tools to analyze syntactic properties of sequences. What are syntactic properties? Are properties that take into account the form of the sequence, the form of a string, and not just statistical properties of it. So the first one I'm going to tell you about is Kolmogorov complexity, which is also called descriptive complexity or algorithmic complexity, which is a notion of information content of a string of symbols over an alphabet. Then I will tell you a bit about conditional Kolmogorov complexity, which is a tool to quantify similarities between different strings. And then I will tell you a little bit about algorithmic randomness, which is a notion of randomness, which is purely syntactic. It takes a string of symbols and it says this string is random or it's not. So it doesn't care about if you could have obtained different results or anything like that. It just looks at the string and says this is random, this is not. And then I will do a short review of some results relating descriptive complexity with quantum correlations. So this will be the way I'll go. Okay, so let's begin with Kolmogorov complexity or descriptive complexity. So the intuition behind this complexity is the following. How long does it take Alice to describe each of these strings to Bob in order for Bob to be able to reconstruct them exactly? Imagine Alice has this string 0, 1, 0, 1, 0, 1, 1 million bits of this, or Alice has this other string, which is 0, 1, 0, 1, 1, 0, whatever. Where, again, 1 million bits generated by tossing a fair coin. If she has to describe these strings to Bob, which will be simpler to describe, which will be easier to describe? So it's easy to get convinced that the first one is easier to describe because she can just tell Bob, write 500,000 times 0, 1. So in just a second of a phone call, she can describe the string. However, the second one is more complex because in order to describe it to Bob, she has to tell Bob every single bit from the string. So this is the notion we want to capture with Kolmogorov complexity. So let's try to go towards a more formal definition of it. So assume we have a Turing-complete programming language L. What's a Turing-complete programming language? It's any programming language that can simulate a Turing machine. So basically, any programming language we are used to work with, Python, C, or even Fortran that some physicists still use. All those programming languages are Turing complete. So given one of these languages L, we define the complexity relative to such language and note it K sub L, the following function. K sub L of X will be a string, will be the minimum length of a program P. This is the length of the program P between bars, such that the program P outputs the string X. So as you can see, when I'm telling you this is the shortest way to describe the string X because it's the shortest program that outputs that string, okay? So in that way, this is the complexity of the description. The shorter the program, the simpler the string X is. So for instance, if we want to give a bound for the complexity of these million bits that were only 1, 0, 1, 0, 1, 0, and so on, assume we are using the language Python. I chose to use this one. So we have this simple program that outputs that given string, that 1, 0, 1, 0, which is for X between 1 and 500,000, print 0, 1, okay? Of course, the simple program outputs 0, 1, 500,000 times. And if you look at this program, it has 35 bytes, a short program, which is 280 bits. So we know that the complexity of this string is less or equal than 280. Why the inequality? Because maybe there is a shorter program that generates this string. So this is just an upper bound, okay? Because the definition of the complexity is the minimum length of the program that outputs the string. So if there's a shorter than this one, which I think there is, this gives an upper bound, okay? And I'm writing some reference at the bottom, so if anyone wants to go into more details, they can check that out. Okay. So the simple criticism one can have for this definition, but it seems a bit useless because it depends on the language L that one chooses. So if we change the language, most strings will change their complexity. So a nice result in order to see that this is not a big problem is the invariance theorem that says that if we have two different languages, L1 and L2, both Turing complete, then there exists a constant C independent of the strings, such that for all strings X, the difference between the complexity for both of the languages will be less or equal than this constant C. I won't get into details of the proof, but the way to prove it, just to consider a translator program that can translate code from L1 to L2 and vice versa. If we have these translator programs, which one can think of them, it's not too difficult, at least to believe that they exist, to write them is a bit more convoluted, then of course, this invariance theorem says that the complexity won't change that much between languages, okay? So now, given this invariance theorem, let me see, there's a question there, a small question. About this last invariance theorem, how does C depend on L1, L2? For example, can one construct a sequence of programming languages where this distance tends to infinity? I say that between two given languages, this is always finite. Because there's a program that translates between them. Not sure about the sequence in which this gets more difficult every time. I'm really not sure about that. The result doesn't seem correct to me. I could just make a language Python X2 where every sentence needs to be doubled in order to be valid, and they wouldn't be related by constant. Well, I'm not sure about that. Okay, maybe, yeah, maybe it's relative and not absolute. Maybe it's, yeah, I'm sorry. Okay. Okay, I'll go on. So, as this notion of complexity is defined up to an additive constant, it is well suited to compare complexity of the different strings rather than to know the complexity of a single string. Okay? So, there's one big issue with this definition of complexity, which is the following. The Kolmogorov complexity is not a computable function. What does it mean? There is no computer program that can calculate the complexity of a string X. And this is a big issue because this means that even though it's a well-defined quantity, we cannot calculate it. So how can we prove this? Let's assume it is computable. So there is a program of length Q that calculates the complexity of a string X. So then we can write this following program that says for S in the set of strings, if the complexity of S is larger than Q, the program left that calculates the complexity, the Kolmogorov complexity, plus Q prime, which is the length of this program I wrote here, return S. So what we have here is a program of length Q plus Q prime, which outputs a string S, which has a complexity larger than Q plus Q prime. But then the complexity of the program, the complexity of the string is larger than Q plus Q prime, but by definition of Kolmogorov complexity, it cannot be larger than a program generating it, Because the definition of the Kolmogorov complexity is the length of the shortest program. So this is absurd. So there is no program to calculate the complexity, the Kolmogorov complexity of a string. So then what? If we cannot calculate it, what is it good for? Well, first, the fact that it can be calculated by any means, it doesn't mean that it doesn't play a fundamental role in nature. Maybe it does. Maybe somehow nature takes into account this descriptive complexity of the strings it generates. And also, although we cannot calculate it, we can approximate it from above without, although it's not a bounded approximation, by the length of the compression of a string. We just take a string, we compress it with any compressor, just like zip or GZ or anything. And the length of the compressed file will be an upper bound to the Kolmogorov complexity of the string. So even though we cannot calculate it, we can use different kinds of approximations to try to work with it. Okay. So let's move now to conditional Kolmogorov complexity. So we define, first, we define the complexity of two strings, x and y, to the complexity of this encoding function of x and y. What's an encoding function? It's a function that takes two strings and converts them into one, such that they can be decoded with another computable function. So for instance, we can have some form of limited concatenation of x and y, the function that encodes the pairs. By limited, it means that first it says how long is each string, then concatenates them or something like that. And then we can define the relative complexity of string x with respect to y as the length of the shortest program that outputs x given y as an input. So it has access to the bits from y, and we want the length of the shortest program that can calculate x given y. If y was infinite, we can regard it as an oracle. So the program has access to the bits of y for free, and it has to calculate x. So the length of the shortest program that calculates x from y will be the conditional complexity. So two nice properties that this Kolmogorov complexity has. First, subadditivity. The complexity of two strings is less or equal than the complexity of the first plus the complexity of the second plus some constant. Here there's a detail. In order for this to be a constant term and not something logarithm in the length of the strings, there are different versions of the Kolmogorov complexity. This will be for the prefix-free Kolmogorov complexity. For the details, you can just ask me later or see on the reference I wrote a few slides ago. And the other result that we will use is the symmetry of algorithmic information, which is that the complexity of xy is almost equal up to logarithmic terms. So the complexity of x given y plus the complexity of y, which means that basically in order to reproduce x and y, you need the information to reproduce y plus the information to reproduce x knowing y. So these two properties are quite intuitive. They are quite useful as well. So now that we have this notion of information content of a string, let's move on to algorithmic randomness. How can we define a notion of randomness related to strings? So which of these two strings is more random? Again, we have this simple example of 0, 1, 0, 1 repeated many times. And we have this other string, which I don't know what this is. Maybe it came from tossing a coin or something like that. So in a sense, it seems like the second one is more random than the first one, right? It's more complex in the sense we defined before. However, both are equally likely to arise from a fair coin tossing. Both have a probability 1/2 to the length of the string. But we want a syntactic definition of randomness. So we will resort to the same ideas as before. We can easily see here that the first string has more structure than the second one. And we want to capture this idea of lacking structure that the second string has for our notion of algorithmic randomness. So in order to do so, we will resort to Kolmogorov complexity again. So if a string has structure, it could be used to give a shorter description of it. So if we can give a shorter description of it, then it has structure, so we would say it's not algorithmically random. So our definition will be that the string is said to be algorithmically random if its Kolmogorov complexity is larger than the length of the string. So we cannot provide a shorter description than the string itself. That would be a string that is called algorithmically random. And of course, we are in QPL, so I have to say something about the L, which stands for logics. So I will tell you a nice result about algorithmic randomness that has to do with logics. So the thing is that randomness cannot be proven. Randomness defined this way as strings whose description are as long as the string, it can't be proven. So the theorem goes as follows. Given any correct axiomatic system, randomness can be proven for at most finitely many strings. So I will give you an idea of the proof without entering into many details because it's a really nice proof. So let's assume we are given a correct axiomatic system. So the description of the axiomatic system is always finite, so it has k bits. And the computer can start enumerating all theorems. It just takes axioms and modus ponens and starts enumerating all theorems from the axiomatic system. Correct means that it's arithmetically sound, yes. That it only provides truths about what we are describing with that axiomatic system. It doesn't even need to be correct, actually, because it will steal these theorems from the axiomatic system, although these theorems won't be truths from what we are describing with it. So let's consider the following program of length S that receives the axiomatic system as an input. This is a pseudo program, of course, but what it does, as I said, a computer can enumerate the theorems. It just says that for T in theorems, if T is a theorem of the form string W of length Q is random, print W, where Q is a number that is larger than S plus K. So this number Q is larger than the length of this program plus the length of the description of the axiomatic system. So we have a program that the program plus the input has length S plus K, S for the program and K for the axiomatic system. And it's on the output writing a string W whose complexity is larger than Q, which is larger than S plus K. So it's basically writing a string which has a complexity larger than the length of this program plus the input. So that string it's writing cannot be a random string because it's generated by a short program, shorter than the description of the string, shorter than the extensive description of the string. So this is absurd because if the string was random, then the shortest description is the string itself. However, here we found a description which is this program plus the axiomatic system that was shorter than that. So this is absurd, and this comes from the fact that there are no theorems like this one for strings of length larger than the length of the program plus the description of the axiomatic system. So at most, we can prove randomness for a short string, shorter than this program and the length of the axiomatic system, but we cannot prove it for any string, okay? So we have a notion of randomness. The problem is that we cannot prove that something is random in any axiomatic system, okay? So I think this is a really nice result, and I really love this proof. Okay, so what happens when it comes to sequence? What's a sequence? A sequence is an infinite string of symbols. So we need to modify this notion of randomness a little bit. This definition was due to Martin Lev. So what's the definition? We will say that the sequence X is Martin left random if most of its prefixes are algorithmically random. What are prefixes? Are the first bits of the sequence. So we take the first bit of the sequence and we want it to be algorithmically random. We take the first 2 bits, we take the first n bits, and for almost all n, the first bits from this sequence have to be algorithmically random. So their complexity has to be larger than the length of the string. So this will be a definition for sequences of algorithmic randomness. And there's an equivalent definition, which is that the sequence X is Martin left random if there is no lower semi-computable martingale that succeeds on X. Let me explain this because there are many terms I didn't introduce here. So a sequence X is Martin left random if there is no betting strategy. A martingale is a betting strategy that says on each round to what symbol to bet for the next symbol. So we are saying that there is no betting strategy that seeing the first bits from the string can guess the next one and make an unbounded amount of money. And lower semi-computable means that that you can generate computable martingales that tend to the martingale that succeeds on X, okay? So you can approximate better and better computably this martingale, even though it may not be computable. So no computable approximable betting strategy for the next symbol of X will win an unbounded amount of money. If that happens, that means that the sequence is algorithmically random. Okay, so these two definitions are equivalent. Okay, any questions so far? No questions, okay. So now that we have all these definitions of information content of a string and randomness, let's move on how to use this for quantum correlation. So what can we say about quantum correlations by using algorithmic complexity? So there are a few results in this direction. I will briefly talk about a few of them. We'll talk about 4 applications of Kolmogorov complexity and algorithmic randomness for quantum correlations. First is a way to define non-signaling based on sequences. The second one is a way to define non-locality. Then I will talk a little bit about this principle of non-trivialization of communication complexity and how it can be modified to take into account strings. And then something in the line of IID, because now we don't have IID, we have strings that may be correlated. So let's try to define something similar to IID to work with. Okay, so how can we define non-signaling for strings? This was introduced by Stefan Wolf, his paper, Non-locality without counterfactual reasoning. So basically non-signaling would mean that the complexity of Alice's output, given her input, will be more or less the same as the complexity of Alice's output given both of their inputs. So it means that knowing Bob's input doesn't help calculate Alice's output. And the same for Bob. Knowing the other party's input cannot help calculate your output. That would be the idea for non-signaling. And if we assume independence for the rounds, this notion recovers the non-signaling principle for probabilities. But without the assumption of independence, this works on an even more general scenario. So this non-signaling principle, for instance, detects the example I gave at first, where B, Bob's output, was a zipped version of Alice's input. So here you can detect that, because of course you can find out that knowing Alice's input helps you calculate Bob's output. Okay, so this complexity will be low and this may be large. Okay. So this is the way to define non-signaling. But how can we define locality? To define locality, this is on the same paper as before. Let me see, there's a question here. One is encoding only a vague and sharp info like it is an algorithmically random string. For such analysis, we deserve to have a notion of complexity of a string to a given level of vagueness, coarse graining. How to do that? Well, there are different definitions in order to approximate the complexity. First of all, Kolmogorov complexity cannot be approximated with a known bound. So you can approximate it, but you don't know the bound for that approximation. So there are different ways, like resource bounded complexity is one. There's another one which just take the strings and try to compress them to have a notion of how compressible it is. These are all approximations of the complexity. I don't know if this answers your question. I mean, if you cannot compress a string, at least you cannot rule out that it's not random. Okay, if you can compress it, you know it's not random. So this gives you some vagueness of complexity, okay? You try to compress it, you fail, then you cannot rule out it's random, okay? Okay, so in order to define locality, one has to assume a hidden variable in order to reproduce a hidden variable model. So they will say it's on the same arc. You say that sequence non-signaling if there exists a sequence lambda such that the complexity of xy given lambda equals the complexity of xy plus the complexity of lambda, and the complexity of A, of Alice's output given Alice's input and the hidden variable is 0. It means that given X and the hidden variable, it's trivial to calculate A, and given Y and the hidden variable, it's trivial to calculate B, okay? This means that this is a hidden variable model. So that would be the second definition I want to tell you about. So what is it good for to define these notions based on strings and on Kolmogorov complexity? So first, we've seen that we can detect situations such as one box compressing the other box's input or stuff like that. Which these notions, when we just looked at the relative frequencies in order to approximate the probability, were hidden in there. But also, when we talk about probabilities, there is a counterfactual assumption. When we say that we obtained this result, but it was just a probability distribution, somehow we are saying that we might have obtained a different result. However, when we look at syntactic properties of string, like Kolmogorov complexity or algorithmic randomness, we avoid that assumption. We should see what we obtain from our experiment. And we make statements about that. And we don't need to resort to this counterfactual assumption that, well, this is a probability and maybe I could have obtained a different result. So that's an advantage, I think, because you don't need extra assumptions. You just analyze what you got from the experiment. Okay, let's go to the third example on how to use Kolmogorov complexity for non-locality. This will be for communication complexity. Let me first introduce the problem of communication complexity. So communication complexity is another problem that deals an informational principle that can be modified as a non-counterfactual principle. I will show you how to do that. So what's the problem? Alice and Bo would like to calculate the function f, which takes two strings as an input, x and y. So the function goes from strings of length n on the alphabet 0, 1 for Alice and for Bob, and it answers a single bit, 0 or 1. Alice will have access to x and Bob will have access to y. So then Alice sends information to Bob in order for Bob to calculate f of xy. So we will say that the communication complexity of the function f is the least amount of information that Alice has to send to Bob in order for Bob to calculate f. Okay, so Alice takes her string, she does some calculations and sends information to Bob, and Bob has to calculate the function f. So one nice result by Van Damme is the following. Every function can be locally reduced to an inner product, f of xy equals x times y mod 2. So classically, Alice has to send n bits of information in order to calculate this function. So basically, she has to send her whole string. But in this paper by Wim van Dam, it's proven that if they have PR boxes are boxes that are non-local, but they are beyond what can be obtained with quantum theory, then a single bit would be enough for them to calculate the function f. And the way to prove it is quite simple. Basically, Alice and Bob use their strings as inputs for their boxes. So the inner product is this. As these are PR boxes, x times y is equal to a plus b mod 2. So we have a sum of a sum, so we can write it as the sum of a y plus the sum of bi. So Alice just needs to send the result of her local sum to Bob. So this is a single bit that Alice needs to communicate to Bob in order to calculate the inner product. And any other function can be reduced to inner products after local transformations. So basically a single bit is enough for the problem of communication complexity if they have access to PR boxes. So how can we modify this principle in order to take into account strings and Kolmogorov complexity? So this is work in progress I have with Nicolas Ciancalini, who was a student here in Buenos Aires. So what if Alice and Bob had to calculate this function that now takes two strings as inputs and returns a string? So what can we say about the string set that Alice has to send to Bob in order to calculate f? So we wrote the following principle. Let x and y be input strings producing outputs AB on a pair of boxes, and they have a target function f. Then the principle states that any physical system, it has to hold the following. What this says is that the minimum Kolmogorov complexity of the string that Alice needs to send to Bob will be such that with some function g, Bob can calculate using his input and his output and the information he got from Alice, the function f. So the principle states that this minimum complexity will be equal to the complexity of the string of Alice. So basically, in the worst possible function f, Alice has to send as much information as her string has. Okay? Which sounds like a quite reasonable principle. So what does this principle rule out? So for instance, imagine we have a signal in boxes where Bob's output is equal to Alice's input, okay? So if we take the left-hand side, this g will be a function of y and b will be equal to x, y and x. So actually we don't need set for anything. So we don't need Alice to send any information to Bob if the boxes were signaling. So this left-hand side is equal to 0 because the complexity of what Alice needs to send to Bob is 0. However, on the right-hand side, we have the complexity of x. So this kind of signaling boxes are ruled out by this principle. And not only this, any transformation from Alice's input will be ruled out by this. So the output of Bob's box is any transformation on Alice's input that keeps the information will be ruled out by this principle, okay? So this is a principle that we think is reasonable for any pair of physical boxes, okay? So it's inspired on the non-trivialization of communication complexity, but it goes a bit beyond and takes into account this scenario. So finally, the last thing I wanted to tell you about, good on time. So when we are analyzing probabilities, we are assuming IID of the variables we see. So when we are working with sequences, how can we state something similar to that of the rounds being independent? So what we can have as a principle would be the following. We want, or not as a principle, as a way to describe rounds that are somehow independent. We will want the outputs to be as random as possible as long as they are compatible with a given probability P of AB given XY. So a bit more formally to go into this, which is again work with Nicolasi and Caglini, we want no lower semi-computable martingale with respect to this probability of AB given XY to succeed on the outputs given the inputs. So basically, if we are playing the game of betting on the next outputs, knowing the inputs, we won't be able to win an arbitrary amount of money. This means that we are having outputs that are as random as possible. So I have another question. Have you explored how your principle relates to information causality? Not much. We know that if we have functions with a single bit, it's the same, but no, not really. It's usually kind of difficult to go from this complexity to probabilities unless you are on really simple cases in which you assume IID. If you assume IID, you can calculate the complexity or something like that. If you don't have that assumption, it's really difficult to go from one to another and prove this relation, at least as far as I know. So with this, I finish. What we saw during this tutorial is the definition of Kolmogorov complexity and a few properties it has. Then how to define randomness from a syntactic point of view, in particular, what is called Martin-Lev randomness. Then how to use these ideas to define non-signaling and non-locality. How can we extend or modify principles that are based on probabilities to principles that are based on these notions of Kolmogorov complexity, for instance, non-trivialization of communication complexity, and how to recover a notion that goes in the same taste as to independence of the rounds. So with this, I thank you for your attention.
Thank you, Ariel.